Episode 6, Algebraic Expressions and More Factoring. So we'll do some more with factoring today, but we will do it in a slightly different context than we were doing it last time. Last time we were kind of limited ourselves to polynomials. We're going to look at it today in terms of something more general, something known as an algebraic expression. An algebraic expression is an expression involving the operations addition, subtraction, multiplication, that would include a variable raised to a power, division, or a root, right? So all polynomials, right, they just have multiplication by a coefficient and raising something to a power in addition, so they are algebraic expressions. But there are things that are not polynomials that are also algebraic expressions. So the thing I've got here, right, 3x to the 5th minus 2x cubed plus x squared minus 3 over x plus 7 times the square root of x. Right, those last two terms, I can write those terms as a coefficient times x to a power, right? The minus 3x to the negative 1 power, that's minus 3 over x. And then 7 square root of x I can write as 7 times x to the 1/2 power, right? But because negative 1 and 1/2 are not positive integers, this is not a polynomial, but it is an algebraic expression. The cube root of 2x to the 4th minus 8x squared plus 15. Again, I've got roots, powers, addition, multiplication, right? But that's all I have, right? So that's an algebraic function. And then this algebraic expression, 3x minus 4 divided by 2x plus 7, right? That's just a polynomial divided by another polynomial. And that's where we're going to focus most of what we'll do today, on a special class of algebraic expressions known as rational expressions. So a rational expression is a polynomial divided by another polynomial, right? So the one I just looked at, 3x minus 4, that's a first degree polynomial, divided by 2x plus 7, also a first degree polynomial, right? So that's a rational expression. X squared minus 1 divided by x squared plus 1, both of those are second degree polynomials. So this would be a rational expression. 3 divided by x to the 4th plus x cubed minus 5x squared plus 6x plus 1, right? 3 would be a 0th degree polynomial, right? So this would be a rational expression. And then all polynomials would, strictly speaking, fit this definition, right? Because the bottom, you could think of it as a polynomial divided by 1. But strictly speaking, yes, they would fit this definition, but we rarely include that. We usually, if I say something is a rational expression, I'm using it to distinguish it from polynomial expressions. Now, the context of factoring is, right, well, I've got a polynomial divided by another polynomial. I might be able to simplify that if I could factor them, right? So think about this one. Simplify the rational expression 2x squared minus 3x minus 14 divided by x squared minus 4. These are two second degree polynomials. If I could factor either one of those, I might see that they have a factor in common, and then I can cancel that. So let's see what we can do here. Right, we want to look for common factors. The bottom's much easier to factor, right? I hope that jumps out at you that that's a difference of 2 squares. So the bottom I can write as x minus 2 times x plus 2, right? If you FOIL that out, you get x squared minus 4. But there is an important reason why we would want to do that here, because that tells us that when x is 2 or minus 2, that expression is undefined. So that's one of the important things that makes a rational expression different than a polynomial. Polynomials are defined for every real number. Rational expressions don't necessarily have that. Some of them would be defined for all real numbers, but this one is not defined for plus or minus 2. Now let's see if we can factor the top. It'll be 2x plus something times x plus something. if we're able to factor it. Right, so we need now the two numbers there that will multiply together to get negative 14, where 2 times the second one plus the first one will be minus 3. Right, so right, think about that. What about negative 7 and 2? Those multiply together to get negative 14. 2 times 2 is 4, minus 7 is negative 3. So yes, that's going to work. Now, look, both the top and the bottom have a factor of x plus 2, right? So I have x plus 2 divided by x plus 2. That is 1. Please understand that that is the reason and the only reason why I can cancel these, right? X plus 2 divided by x plus 2 is 1, and 1 times something is that something. That is the only reason we can factor these. Don't make up another reason. So that leaves 2x minus 7 divided by x minus 2. But I do need to make a little bit of a caveat there. Because the original expression given to me was undefined at plus or minus 2, this expression can also not be defined at plus or minus 2. Now, the expression that's there, 2x minus 7 divided by x minus 2, that is not defined at 2. But that is defined when x is equal to negative 2, right? I can plug in negative 2 there without any trouble. I get negative 11 divided by negative 4, right? That's 11 fourths, right? No problems there. Except that this thing is equal to this other thing that I had. So I have to include the statement of x not equal to negative 2. Right? We got to be careful about that. We can't take the original expression and then suddenly make it equal to something when x is negative 2. We'll come back to this a couple of times during the semester. All right, let's do another example here. Right, if we're going to simplify x to the 3/2 power minus 8 square root of x divided by x squared minus 7x minus 8. Now, this particular expression is not a rational expression, right? The x to the 3/2 part and the square root means the top is not a polynomial. But I can do what I just did and try to simplify it, right? If we think about the top, 3/2, that's 1 plus 1/2. So x to the 3/2 can be x to the first power times x to the 1/2 power. So that would be x square root of x. And so the top can be written as x square root of x minus 8 square root of x. And so I can factor that square root of x out, and I get that the top is equal to x minus 8 times the square root of x. Hey, well, the bottom, I need factors of negative 8 that add together to get negative 7. That would be 1 and negative 8. So the bottom is equal to x plus 1 times x minus 8. Hey, there's an x minus 8 as a factor in both the top and the bottom. X minus 8 divided by x minus 8 is 1. And so that means I have square root of x divided by x plus 1 as long as x is not equal to 8. And so we've simplified that algebraic expression. I'd like to spend the rest of the day talking about a technique that is motivated by what we do when we see an improper fraction. Right, 17/5, right there. I'm saying that is an improper fraction because the numerator is larger than the denominator. There's nothing inherently wrong with writing something in this form, and to be honest, if this number were the answer to a question, I would want you to give it to me in this expression, right? 17/5, that's a perfectly fine thing. But we do need to know how to get it into a form that's not an improper fraction. We can write this as an integer plus a proper fraction. The way we do that is by thinking of the largest multiple of 5 that is less than the numerator. That is, we use long division, right? So how many times does 5 go into 17? That would be 3 times, right? So I take 3 and I multiply by 5, and then I write that below the 17. That is 15. And then I subtract. And when I have 2 left over, that is known as my remainder. So I'm going to write 17/5 as 3 plus 2 to the 5th power. Please do not write that without the plus sign. That 3 and then 2/5, that's kind of an ambiguous notation, right? If I see that, I really think that's 6/5, right? 3 times 2 is 6. That's not what you mean when you write that. And so that's kind of an ambiguous notation. It can mean both 3 plus 2/5 and also 3 times 2/5. And so we need to make sure that we are not ambiguous. All right, so leave it as the plus. All right, so I bring this up because there's the idea of an improper rational expression. That would be a rational expression with a polynomial divided by another polynomial. It's improper if the polynomial in the top is of a higher degree than the one at the bottom, right? So this one here, we've got x cubed minus 5x squared plus 3x plus 9. That's a 3rd degree polynomial, and I'm dividing it by x minus 3, a 1st degree polynomial, right? So this is an improper rational expression. Now, again, it can be perfectly fine to use this, but we may be able to simplify this or write it as a polynomial plus another rational function that's a proper rational expression. Let's figure out how to do this. So that particular example, I want to try to simplify it. Now, it's kind of difficult in general to factor a cubic polynomial, but I can just see quickly that if I plug in x equals 3, I get 0 in the top, right? Why did I pick 3? Well, that was what made the bottom 0. Because I plugged in x equals 3 and I got 0, that means I will be able to factor an x minus 3 out of the top and cancel it with the bottom. So I know that I can do that. This is a good thing to talk about in class if that is not obvious to you. So think about it a little bit, and then we can talk about it. Now, the more important question for what we're doing right now is, I know that I can factor it. That doesn't tell me what the other factor is. So I need to find a polynomial that when I multiply it by x minus 3, I get x cubed minus 5x squared plus 3x plus 9. Right? So there's a technique for doing this called polynomial long division, right? And we've kind of mimicked the steps of regular long division. So what I want to do first is think about what do I need to multiply the x in x minus 3 by to get x cubed? Well, that's not too hard, right? That's just x squared. So I write x squared above the x squared column there under the division sign, right? So and then I multiply x squared times the thing that I'm dividing, right? X minus 3. So that's going to be x cubed minus 3x squared. And the next thing I do is subtract. So what do I have left over when I subtract? I have the x cubes cancel because I constructed them precisely to do that. And then I got to distribute that minus sign. So I've got minus 5x squared plus 3x squared. That leaves me with minus 2x squared. Okay. So now I just repeat the process. Right, I'm going to bring down this next thing here, right, plus 3x. And then I need to now figure out what do I multiply x by to get minus 2x squared? Well, that's going to be minus 2x. Right, so that's the next term in this factor. And then I multiply again here, right? So we got minus 2x times x minus 3. That's minus 2x squared plus 6x. And then I'm going to subtract. Again, the minus 2x squareds cancel because I built them to. and then 3x minus 6x is minus 3x. I bring down the 9. To get minus 3x, I need to multiply by minus 3, right? Minus 3 times x minus 3 is minus 3x plus 9. Now, look at that, right? So when I subtract, I get 0. So that's my remainder. My remainder is 0, which means that this is, in fact, a full factor, right? What that means is I can factor the top, x cubed minus 5x squared plus 3x plus 9. That is equal to x minus 3 times x squared minus 2x minus 3. And I can simplify that, right? X minus 3 divided by x minus 3 is 1. So I have, I'm left with x squared minus 2x minus 3, as long as x is not 3. Right? If x was 3, my original expression was undefined. Right? Now, that polynomial, x squared minus 2x minus 3, I can factor that. Right? That factors into x plus 1 times x minus 3. Right? I can use polynomial long division to factor this. If I know what one of the factors is, I can use that to get the other factor. Right? Let's do another example. I want to write 3x to the 4th minus 7x cubed plus 6 divided by x squared plus 1 as a polynomial plus a proper rational expression. So in the previous one, my remainder was 0, so I could write that one as just a polynomial. Here, I'll tell you right away that it's going to be a non-zero remainder, but I can tell you two things. I know that the polynomial that I'm going to end up with will be a second-degree polynomial. I know that by looking at the difference between the highest powers in the top and the bottom. Right? I have a fourth-degree polynomial divided by a second-degree polynomial. That means the resulting power is going to be 4 minus 2, 2. And then the remainder always has to have a lower degree than the bottom. So it's got to be lower than 2. So that means it could be a first-degree polynomial or a 0th degree polynomial, just a constant. All right, so I need to divide x squared plus 1 into 3x to the 4th minus 7x cubed plus 6. I've skipped some space in there because I need to fill in with 0x squared plus 0x. I need all of the powers to be present. In part, that's just so that there'll be the appropriate amount of room in the top. All right, so where do we start? We think about what do we multiply x squared by to get 3x to the 4th? Well, that's going to be 3x squared. So when I multiply 3x squared times x squared plus 1, I get 3x to the 4th plus 0x cubed plus 3x squared. So when I subtract, I have minus 7x cubed minus 3x squared, and then I'm going to bring down the 0x. So now I need to multiply something by x squared to get minus 7x cubed. Well, that's going to be minus 7x. So multiply by x squared plus 1, I get minus 7x cubed plus 0x squared minus 7x. And I subtract this, and I have minus 3x squared minus 7x is plus 7x. And then I bring down the 6. So I need to multiply by minus 3. So that's minus 3x plus 0x minus 3. Now when I subtract, I get 7x plus 9. That's something that's lower than second degree. So my remainder is 7x plus 9. Now what do I do with that? Right? In my previous example, I had a remainder of 2 when I was dividing by 5. So I had a plus 2/5. And I did the same thing here. Right? My remainder was 7x plus 9. So I'm going to divide that by the thing I'm dividing by here, x squared plus 1. So I can write the rational expression that I had up there, 3x to the 4th minus 7x cubed plus 6 divided by x squared plus 1. I can write that as the polynomial 3x squared minus 7x minus 3 plus the remainder term 7x plus 9 divided by x squared plus 1. Now, a little bit about why I would want to do this, right? When we get to talking about trying to understand how a function behaves, how an expression like this behaves, how an expression like this depends on x. Well, here it's a little bit easier to think about, right? Because if I let x be really, really big, x squared plus 1 is going to be a lot bigger than 7x plus 9. So that last term there can be kind of irrelevant, right? If x is big, the bigger x is, the more this expression behaves like 3x squared minus 7x minus 3. Right? That's going to be much easier to understand than the way the thing was originally given to us.